For the first part of the homework problem, you're asked to find the initial acceleration of the electron. So let's remember Newton's second law says that the net force on an object is mass times acceleration. That tells us that the acceleration is the force divided by the mass. The force we found in the example problem, 8.14 times 10 to the minus 11 newtons in the j direction or up. Divide that by the mass of the electron, 9.11 times 10 to the minus 31 kilograms. And we get an acceleration of 8.94 times 10 to the 19, yes, 19 meters per second squared straight up. Something that's a little bit interesting here is the phrasing of the question. I said find the initial acceleration. Why initial? Well, if my electron starts here and it has an acceleration that pulls it upwards, it's going to start to move up. As it moves up, the distance relative to the charges changes. It's not the same as it was at the very beginning. So if the distance changes, then our force changes. If the force changes, then the acceleration will change. So this electron will actually have a varying acceleration as we go. Technically, it's something you could calculate, but it's a little advanced for this course, so I would only ask you for the initial acceleration. Okay, I'll go to a fresh slide to do the second part of the homework, which is what happens if we swap the electron with a proton. We can use symmetry to answer the second part of the homework question as well. Find the net force and acceleration if we had a proton at the center of the square instead of the electron. So we won't go through the entire process, but if I have a plus here, a plus here, a minus here, a minus here, there's the four charges, and I put my electron at the center. Let's look at what the free body diagram would look like. It would be repelled by the positive charges, and it would be attracted by the negative charges. So the free body diagram is kind of interesting. So that would be F1, that would be F4, that would be F2, and that would be F3. So those forces are all in the opposite direction compared to what they were for the electron. Let's think about the magnitudes of those forces. The charge on a proton is plus E. The charge on an electron is minus E. Those charges are equal and opposite. So the four charges, Q1 through 4, they stay the same. The four distances, they all stay the same. But the charge that's feeling the force, the proton, the sign of that charge switches. It goes from negative to positive. So the charges are equal and opposite. That means the forces are also equal in magnitude, but opposite in direction. So the force is equal and opposite. So if the force on an electron is up, the force on the proton is down. So the forces depend on the charges and the distance. With the opposite sign charge, we get the opposite sign force. What about the acceleration? Well, we use F equals ma. So A equals F over m. Here we expect something different because the mass of a proton is different from the mass of an electron. So let's put in our force, minus 8.14 times 10 to the minus 11 J in newtons, divided by 1.67 times 10 to the minus 27 kilograms, gives us an acceleration that is minus, so it points down. That makes sense because the net force is down. 4.87 times 10 to the 16 meters per second squared J hat. So this is a smaller acceleration, but still very large.